All right, guys, how are you? We are going to answer a couple key questions in this discussion for this chapter. Where is the Earth? Where is Earth in the universe? So, kind of, where is our place? I've talked about this before. We're going to talk about how human history fits into the history of the universe, and then why to study astronomy. I'm going to skip forward a couple of slides. Bear with me as we go through this. There's a couple of questions and stuff. We'll come back to those later. But to get in there, where are we? So there's a video I posted that you're going to want to check out. It's called Powers of 10, and it basically zooms out. It looks like this, and it's going to zoom out in powers of 10, all right, every single time. So multiplying by 10 each time, zooming out in the universe, and you're going to find out kind of where we are based on that. So you'll see how that zooms out. We're going to add a couple of slides here for that. Zooming out by a factor of 100. We zoom out not from just that park bench, but now you can kind of see what is going on with that. You can see where it's at. I thought I had a pointer here. Anyway, that park bench, I believe, is somewhere right in here. All right, but now we're zoomed out by just a factor of 100, so that's another power of 10. All right, and as you get further and further out, you start to see the vastness of the universe with that. Field of view 160 kilometers wide, and this is in the infrared view. You can kind of see what's going on here. Our planet shows up as red. Our eyes are only sensitive to a certain narrow band of colors. We're going to look into that. You can only kind of see in the visual spectrum, and we're going to talk about that because a lot of what we see in astronomy is observational, and so what we're going to be seeing is going to be with your eyes. And so we can't quite see all of that. If we come all the way out to about 13,000 kilometers in diameter, that's the Earth. We can see a visual of what the Earth looks like. And if we were to zoom out as far as that goes, we would see we'd be able to see the Earth in the full view. All right, you can see, kind of noticing on the side over here where there's a boundary. You can see the boundary between day and night right along this edge here. All right, and that edge is showing kind of where day and night is, and as the Earth rotates, all right, this away, more of it becomes in the dark, less of it in the night, and the Earth rotates around that direction. All right, kind of starts to look blurry. You can kind of see what's going on there, and you can actually see the rotation at this distance. Backspace. Here we go. Earth and the moon. Now we go out to a bigger field of view, and you can see the Earth and the moon and the relative size as it's gets enlarged, and you can see the whole orbit as you go. So just gives you an idea of what's going on here. We talked about in class today an AU, astronomical unit. That's the distance between the sun and the Earth. You can see that at this view. As we go out even further, you start to see the whole solar system. We won't spend a whole lot of time on that because it's kind of elementary. We're going to get into deeper stuff. But my very educated mother just served us. I like to use nachos. It says noodles here in the slideshow. But my very educated mother just served us nachos. I like nachos better than noodles, but if you like noodles, that's cool too. That you can remember the order of the planets. That's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. All right, and Pluto obviously got knocked off there. We'll talk about that as well. It's actually added back on now, so that'll be interesting to hear what that reasoning is. As we get out to even further away at 11,000 astronomical units, that's 11,000 times the distance between the sun and the Earth, you start to see that most of the space is empty. In that video you're going to watch, it's going to talk about that. A little bit more why that is. We are really the exception of all the activity that's going on or that has happened in our solar system. A few million AU, we start to see a little bit more of what's going on. We start to see a little bit more of reaching out to bigger distances. This is the distance that you would use, that distance of a light year. We'd start measuring things in that. The sun is the center. There's a couple of near stars. The distances are much greater. We use the light year as the distance. That's the distance that light travels in a year. It's about 1,013 kilometers, or 63,000, astronomical units. These dots that you see, which you'll see on your sky map as well, the dots do not represent the size, but rather the brightness. So we're going to talk about that, size and brightness versus even the distance from the Earth when you're looking at stars. Is that how they seem in the sky? A lot of what we're going to talk about is how do things look from the Earth and what's actually going on, and how can we sort that out between with science. So a question for you to kind of pause and ask yourself this question is, and you may have already know this, is light year a unit of time? I'll pause there for just a second, let you contemplate that on your own. A light year is not a unit of time. A light year is a unit of measurement of distance. And with that being said, it is the distance that light travels in a year. The reason we can use that as a measurement is because light travels at the same speed no matter what. Well, in a vacuum, I should say. So with nothing around it, in the emptiness of space, or the almost emptiness of space, light travels the same speed. All right. There's some theories about like gravity affecting this and some other stuff that's kind of interesting and cool when you get into it deeper. But I just want to make that point that light year is not a unit of time. Do stars look like disks when viewed through a telescope? So stars are really so far away that we really only see them as a point. They don't really show up as a big disk. We can't see the whole thing. You can tell this very easily with just a very basic telescope if you get a chance to do that. Hopefully we can be back in person sooner than later, and I can kind of organize the time to come up to the school, bring my telescope, and do that. There's usually an astronomy at the beach thing that happens, and it'll be happening virtually coming up pretty soon. Hope I didn't miss it. And I'm going to give you guys the link to see what's going on there. But usually you go out and there's tons of telescopes. People bring them from all over, and you can see from there. But even the point of light, even when we look through a telescope, it still looks like a point of light. The point gets a little bit bigger and maybe a little bit fuzzier, and maybe a little bit sharper, but it still comes out as a point of light. You can tell this, what I was saying is the way you can tell this is looking at a planet through a telescope versus looking at a star. Even when you bring the star in closer, it still looks like a point because it's so far away. Now, planets, when you bring them in closer with the telescope, you can start to see they do look like a little bit like disks, and so on. Can we see planets orbiting other stars using a telescope? Pause for that question. The answer is that no, planets are much too small, too dim, and too close to their stars to even be seen most of the time. You can't really they're not really visible. We see them as, and like we found exoplanets, we see them by their shadow that they cast on the sun, actually. They're nothing more than kind of a faint point that goes around their star. As they go around their star, they kind of block it out for a minute, and we see these fluctuations of light that are periodic, meaning they always happen kind of with the same frequency. They come by, once every whatever, a year, 2 years, 10 years, 12 years, and so we start to notice that there's there's something there. So you start to see that must be a planet. So going out even further, 1,700 light years. See how I am on time. I need to wrap this up. 1,700 light years out, and you start to see even more stuff. You start to see galaxies and differences and different areas of the sky like that. 170,000, you start to see our entire galaxy. Our entire galaxy is out there. You'll see this in the video as well, but we jump out, you see the Milky Way galaxy amongst other galaxies out there, and they form these chains and these local clusters, all right, and kind of in the neighborhood. And our last view is really the entire universe kind of strung together, all these collections of galaxies. This is huge. These are all little galaxies that you see. You see all these these are clusters of galaxies. There are multiple galaxies in that little spot, and they form these like this fabric of time that kind of weaves in and out and around. All right? Those are all just different galaxies, clusters of galaxies, multiple galaxies in all of these little dots that you see. Our universe is huge. That's the point. We'll talk about when is now. We'll talk about that next time. So where is now was this video. The next video will be when. So we'll talk about time.